In the previous video, we looked at a mass attached to a spring, and we analyzed the behavior and realized that it follows a second-order linear constant coefficient differential equation, and we already know how to do the homogeneous versions of those, so we applied that. One thing I forgot to mention in that video, and I'm mentioning it now, is just a term. The mass on a spring, or anything that moves in a similar way, anything that follows one of those Hooke's law type forces, where the force is sort of always wanting to pull you back to the center, and it has a magnitude that is proportional to how far away you are from the center. Right? That was Hooke's law for a spring. That situation comes up a lot, and any situation like that, where you might also take into account a damping force and then maybe other forces, is called a harmonic oscillator. So I just wanted to get that term out there so that when you see that in problems in the text and so forth, you know that that's what's being talked about. Harmonic oscillators include other things besides masses on springs, but that's sort of our prime example. All right, now in this video, I just want to add a quick little note about that. Let's imagine a vertically hanging spring, and I want to throw that into the mix, and I want to show you that in essence the analysis is no different. But to see that it's not really different in the long run, we have to just make a couple of connections. So here I have the spring just hanging on its own, and that, let's call that x equals 0. Well, when we attach the mass to the spring, of course, what happens is that it gets stretched, and that's because of gravity, right? So gravity is going to pull it down. And let's say that here is the place where the mass would hang and simply sit there without any going up and down motion. So let's assume that that's the case, and let's call that negative h. So attaching the mass to the spring caused the spring to be pulled down, to be stretched by a distance h. All right, well, if we look at F equals ma, and we account for all the forces, we still have the spring still works the same way, whether it's horizontal or vertical. So we still have a negative kx. We have potentially a damping term, minus b dx dt, right? We might have friction. We might have other forces, although we haven't dealt with those yet. But then now we also have gravity. Now gravity is always going to be downward, and again, if you remember a little bit of physics, gravity is m times g, at least if you're working near the surface of the Earth, where g is the gravitational constant 9.80. Okay. Well, if I, again, move the x stuff over to the left, I get m times the second derivative plus b times the first derivative plus k times x itself. And then I get equals minus mg, and then minus the other stuff. Okay, but let's go back to this picture, right? So when this block is just sitting there, not moving, that must mean that, okay, the spring is being stretched, right? So the spring is trying to pull this block up, and that would be k times h, right? Because it's being stretched at distance h. It's actually negative h, so negative kh. It's positive kh. It's pushing it upward. But of course, gravity is always pulling downward. But if this is where the block comes to rest, then that must be where kh and mg are balancing each other perfectly. So we have that kh equals mg. So in my differential equation so far, I can replace minus mg with minus kh. Okay. So there we are. Now, I'm going to do the following. I am going to change how I'm measuring position, right? We measured position originally with a variable called x, and we set the 0 point to be where the spring is at rest when there's no mass attached. But what I'm going to do now is I'm going to shift that, and yeah, I'm going to make the new position variable y, and I'm going to set it to be 0 where things are at rest when the block is attached. So right here will be y equals 0. And then this would be y equals positive h, and up from there, and of course negative would be down from there. So I'm just shifting the 0 position from here down to here. If you think about it, what I'm doing is I'm saying, so y is x plus h, or to rearrange that, x is y minus h. And now it's going to sound like a bigger deal than it really will be. I'm going to rewrite this whole differential equation in terms of y rather than h. Now, I replace x right here with y minus h. Now, there is no x or y on this side, so that's all the same. Now, how about the derivatives? Well, we're actually in good shape here, because if you look at this, if you imagine taking the derivative of both sides, the derivative of x, right? Derivative of x is derivative of x. And then if I take the derivative here, I get the derivative of y with respect to t. And then this is a constant, right? H is just this amount that it's stretched by when we attach the mass. It is a constant, so the derivative is 0. So in other words, x and y have the same first derivative. So I can just replace dx dt with dy dt. And of course, the second derivative, same deal. So that was easy. So the only change was right here in the differential equation. Just the x itself got kind of shifted when I change x's to y's. Now, why do I want to do that? Well, in the differential equation, notice I have plus ky, and then I have minus kh. And I have minus kh over here as well. And so the minus kh's cancel. And so my final differential equation, in terms of y now, in terms of this new position scale, ends up being exactly the same differential equation as when we did the horizontal spring. So, same as before. This is good news. This means we don't have to analyze this vertical spring in, like, we don't have to reanalyze it. It's all the same as when we analyze the horizontal spring. And so we can summarize the lesson we just learned by saying vertical springs behave the same as horizontal springs. You just have to use a position scale where your 0 is set to where the spring stretches to when the mass is attached, not where it is when the mass is not attached. If you just set your 0 point to that place, you don't have to do anything different. The differential equation is the same, and therefore all the solutions are the same, and it's just as long as you stick to that scale, that y scale, as opposed to that original x scale, everything is fine. So nothing changes. And in fact, you don't, the gravity is already taken care of. Gravity is already built into it, baked in. Notice that our final differential equation, the mg is no longer there. We kind of worked it out and then got rid of it through this change to y. So it might look like, oh, we're not taking gravity into account anymore, but we actually have. It's just kind of baked in now.